This is Organic Ketones. Welcome to my YouTube channel where I teach tricks and tips for chemistry or on chemistry. So if you want to see more of my videos, why don't you subscribe so that you can enjoy, because the more you subscribe, the more rates you'll be able to see my videos when posted. Thank you. So in today's video, and one more thing, if you are a first timer here, kindly subscribe, but if you are not, just stick around and watch. So in today's video, I will be teaching you guys how to use Slater rule to find the effective nuclear charge of an element. This particular topic here is very complicated. If you are new to this topic, you have to listen very attentively and try to make sure that you have your pen and your notes, so that as I communicate, you tend to write it down and tend to understand it the more, because it is very, I won't say very, it is somehow complicated. So, and the reason why I'm not going to use very, because you can understand it, it's something you can understand. So I start now. According to Slater research, that electrons in a main shell will be reduced by 0.35 in its nuclear effective charge. And what do I mean by a main shell? For example, if you have lithium, right? Lithium is 3, right? It's going to have 1s to 2s1. This last one here is going to be the main shell, and it said that it will reduce by 0.35, and he also said that there will be loss of electron, and that loss of electron will be one loss of electron. So that means this place, which is the main shell, will be our N. So any one before it, N1, before that one, if there's anyone before that one too, it will be N minus 2. If there's anyone before that one too, it will be N minus 3, like that. So that is what we are going to be looking at into this video. So if you check this table here, it says electrons in orbitals S or P, the N, which is the main one, will be reduced by 0.35. The one in the N minus 1, I told you it will be reducing, that will be 0.85. The one in N minus 2 will reduce by 1.00. And for the D or F orbital, the N, which is the main shell, will be reduced by 0.35, while others will be 1. So it is also explained in this sphere. I know that you guys are familiar with this sphere. So any electron that falls here, according to the D and F, we have 1. The one that falls here, 1. The one that falls here, 1. The one that falls in the main shell will be reduced by 0.35. And then this sphere is also what I explained in this table. So if you understand this table, you can also understand this one. So it's very simple. And the formula for calculating effective nuclear charge is this: Zef is equal to the Z. The Z represents the atomic number minus the screening constant. And that screening constant is what I'm going to be teaching you on how to calculate it. When you know the screening constant, then you can just remove it from the atomic number, then you get the effective nuclear charge. And we are starting right now. So if you look at this rule, normally if you want to write our electronic configuration, and if you check this, it's a kind of grouping. 1s will stand on its own, 2s and 2p will be grouped together, 3s and 3p will be grouped together, 3d and 4sp will be grouped together, 4d will be grouped alone, 4f will be grouped alone, 5s, 5p will be grouped alone also. And one thing you should understand, that normally if you want to write electronic configuration, you used to say 1s to 2s to 2p6, 3s to 3p6, 4s to 3d10, right? Though it is very cold, but here you have to arrange it like this. This 3, make sure that you've gotten your 4s2, make sure that it's this 4s2 that you first find. But when you now want to arrange it, you now put this one in the front. Normally this one will be before it when you are writing it, but when you want to arrange it, this one will be here. So, and we're going to start right now. So the first element we are going to be looking at here is lithium. Lithium is having atomic number 3, right? So, and that one is 1s2 2s1. This is the main shell, right? And this one is the other one. And I told you that there will be loss of one electron in that main shell, and the main shell will be reduced by 0.35. So we are assuming, we are know, according to rule, we know now that this 1 will become 0. And if you check n, and this is also an s orbital, and from our table here, it says s or p that falls in electron that falls in s or p orbital and has the n, we have 0.35. so this one will be 0 times 0.35. so this one is n minus 1. If you check here, n minus 1, it says s or p, anyone that falls in n minus 1, we have a reduction of 0.35. you put the 0.35, and this 2 electron that is here, so that will be 2 times 0.85. sorry, so this one will experience 0.35, this one experience 0.85. so when you do this now, this one will turn to 0, and 2 times 0.85 will be 1.7. so this is 1.7. so I'm sorry guys that I had to change the page, something happened. So the value is 1.7. the value that we calculated there was 1.7. so the screening constant is 1.7, which is the one we calculated here. So let us now look for the ZEF, and from the formula it says Z minus screening constant, and this is the screening constant right here. So, and Z is representing the atomic number. So what is the atomic number of lithium? That is 3.0 minus 1.7, and that give you 1.3. so the ZEF, which is the effective nucleic charge of lithium, is 1.3. so let's move to the next element here, which is beryllium. That will be 1s2 2s2. so this is going to be our n. Don't forget, this one will be our n minus 1. And if you remember what I told you, I said that there will be loss of electron here, right? If you remember. And I also told you that any electron that falls in n minus 1 will experience 0.85. the one that falls in n will experience 0.35. so that is what we are going to apply right now. So this one will be, since it's going to be reduced by 1, so this one will just be 1 times 0.35. this one will be 2 times 0.85 plus, so this one will give 1.7 plus 0.35, and that will give you 2.05. so this is the screening constant here. So the ZEF will now be 4 minus 2 point, and that will give you 1.95. so 1.95 is the ZEF of beryllium. So let's move to the next element here. Let's go to calcium. Calcium is 1s2 2s2 2p6 3s2 3p6 4s2. so calcium ends at 4s2. so this is going to be our n. And don't forget the grouping, this grouping that I said 2s and 2p will be together. So don't forget this grouping, and we're going to be using these groupings right now. So we'll group them. So we've grouped this one together, this one is separate, this one is separate, this one is separate. So this one will be our n minus 1, n minus 2, n minus 3. so this one will lose one electron because it's the main shell. It is the last one, so this one will lose one electron, so it will be 1 times the value. This one 2 plus 6, 8 times. This one will be 8 times also. This one will be 1 times. So let's now input the values according to the table. So I'll show you guys the table right now. You see the tables. It says when it falls in anything n minus 2, n minus 3 for the s or p orbital, anything that falls in n minus 2, n minus 3, n minus 4, n minus 5, they are going to be experiencing 1 1 1 1 1. So do you understand? So anything from n minus 2 now is just going to be 1, and anything n minus 1 will be 0.85 for the s or p, and anything will be 0.35. We're going to be inputting those values right now. This one will be 0.35, this one will be 0.85, this one will be 1, this one will be 1. So plus, no, sorry, this one will be 2 because the electron is 2. I'm sorry, 2 times 1. This one electron is 8, this one electron is 8, this one electron is 1. So 2 plus 8 plus 8 times 0.85, I think that will give you 6.8 plus 0.35. So 2 plus 8 will give you 10. 10 plus 6.8, that will be 16.8, and 16.8 plus 0.35 will give you 17.15. Do you understand how I did that? So let's now calculate for the zelf. Zelf will now be 20 minus 17.15, and that will give you 2.85. So that means the zelf for calcium is 2.85. So let's check for the last one. That one, since that one is having atomic number 38, so it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s, no 5s2, yeah, 5s2. And don't forget the grouping. So this in the rearrangement now, so this 3d10 will come before this, so let's rearrange that and group it. So let's group that. So we've seen the grouping already. So this will be our n minus 1, n minus 2, n minus 3, n minus 4, n minus 5. Even without checking the table, to make our work very easier, let us add everything here together and multiply times 1, because everything will be 1. Let's add everything here. After adding them, because this one is 10, 18, 26, 28, so this one, let's say 28 times 1 plus, so it now remains this one and this one. So this one falls in the second, it falls in n minus 1 for the s and p, and from the table it says anyone that falls in s and p, it will experience 0.85. so this one will just be 8 times 0.85 plus, so you know that this one is the main shell, so there will be reduction, so this one will just turn to 1. So instead of using 2 times, it will be 1 times 0.35. so this one will give you 6.8, 28, 0.35. If you do everything, I think it will give you 35.15. so that is the squeezing constant. So let's calculate the zelf. The zelf will be 38
minus 35.15, and let's calculate that will be 2.85. Yeah, I think it will be 2.85. Because 85 plus this, okay, yeah, that's 2.85. So that is the end of today's session. If you like my video and you like what I'm doing, why don't you support me by subscribing? See you next time.